Hey everyone, welcome to my YouTube channel CAIE Science, and today we will be solving my June 2022 paper 42 of 9101. Okay, let's begin. Question number 1. The solubility of group 2 hydroxide increased down the group. Explain this trend. Why the solubility of hydroxide increased down the group? Because the lattice enthalpy and the hydration enthalpy becomes less exo. And why they become less exo? Because the charge density down the group decreases. Okay, so uh, that's why these lattice enthalpy and hydration enthalpy, they both decrease, but the hydrogen enthalpy decreases less, or you can say the lattice enthalpy changes more. Okay, so this solution becomes more exo, the solution enthalpy change of solution. Okay, so we'll write lattice enthalpy and hydration enthalpy both become less exothermic. Okay, why? You can write the reason, but this the reason is not that necessary. Okay, according to marking scheme, so the lattice enthalpy and hydration enthalpy both become less exothermic, and lattice enthalpy changes more. So the solution enthalpy, so the enthalpy change of solution become more exothermic. Okay, the lattice enthalpy and the hydration enthalpy are both negative. Okay, they will always be negative. Okay, they will be negative, but the solution enthalpy change of solution, it could be positive or negative. And when this enthalpy change of solution is negative, it means the reaction is the compound is soluble. Okay, and this, when this is positive, it means that the compound is less soluble or insoluble. Okay, so here the enthalpy change of solution becomes more exothermic, so it means it is becoming more negative, so means it will be more soluble down the group. Okay, and the equation which relates these is the enthalpy change of solution is equals to hydration enthalpy minus enthalpy change of lattice enthalpy. So this is the equation which relates these three. Okay, moving towards next part B. The solubility of barium hydroxide in water is 2.4 into 10 to the power minus 6 gram per dm. Write an expression for the solubility product KSP of barium hydroxide. Okay, so firstly you will write what will be formed when barium hydroxide becomes soluble. Okay, so it will form barium ions plus OH ions. Okay, so now the equation will be the concentration of the definition of solubility product is the product of concentration of ions of sparingly soluble salt at equilibrium. Okay, so it will be barium 2 plus ions, concentration of barium 2 plus ion, then OH negative, concentration of hydroxide ion, and there are 2 moles, so the moles will be in power. Okay, and state its units. Okay, so the units will be mole cube per dm cube minus 9. Okay, because the concentration is in mole per dm cube, so these the square will make it a mole square dm cube minus 6, and it will multiply with mole per dm cube, so it will be mole cube and dm cube minus 9. Okay, so this is the units. Okay, calculate numerical value of ksp. Okay, so the formula is given, which we have make. So now I'm writing again this equation here. So when barium hydroxide becomes soluble, by the way, this reaction is reversible. Okay, it forms barium 2 plus ions plus OH ions. Okay, so if you think that if X moles or X concentration of barium hydroxide is um, soluble, so X moles of barium 2 plus ions will form and 2x moles of OH ions will form. Okay, let's suppose when 1 mole of barium hydroxide is soluble, 1 mole of barium 2 plus ions beryllium 2 plus ions beryllium 2 plus ions will form, and then 2 moles of OH ions will form. Okay, I hope it's clear up to this point. Now let's see, if the I say the concentration of beryllium 2 plus ions is X, and the concentration of OH is then 2x. Okay, so ksp is equals to x 2x. X is the concentration of beryllium ions, and then OH is the concentration of 2x is the concentration of OH ions, and then it will be square, so it will be 4x cube. Okay, you understand that? And now you are given the solubility of barium hydroxide, so which is X. Okay, barium hydroxide. Okay, but this is given in gram per dm cube. Okay, so firstly we will convert this value into mole per dm cube, and for that we will divide this 2.4 into 10 to the power minus 6 by the mr of beryllium hydroxide. So let's calculate this. 2.4 into 10 to the power minus 6, and the mr of beryllium hydroxide is 43. You can calculate it from calculator. It will be 5.58 into 10 to the power minus 8 mole per dm cube. Okay, and this is in the X. Okay, the solubility of beryllium hydroxide. Okay, so ksp is going to be 4 into 5.5 into 10 to the power minus 8 and cube. Okay, so it will give you the final answer of 6.95 into 10 to the power minus 22. Okay, so this is your answer, 6.95 into 10 to the power minus 22. Okay, this is the value of ksp. Moving towards next part. Beryllium hydroxide is soluble in aqueous solutions containing an excess of hydroxide ions and forms this complex ion. Okay, this complex ion has a similar shape to that of this copper complex. Okay, and this copper complex has shape of tetrahedral. Okay, you have to remember that. Define the term complex ion. Okay, what is meant by complex ion? Basically it's an ion in which central metal atom is surrounded by ligands through dative bonding. Okay, an ion in which central metal atom metal atom or ion. Central metal atom or ion is surrounded by one or more ligands through the dative bonding. Through dative bonding. Okay. So this is the definition of complex ion. Okay. Draw a three-dimensional diagram to show the structure of complex. This complex, name the shape. Okay, so the shape is tetrahedral. Okay, tetrahedral, because it told you that it has a similar shape to that of this complex, and this complex has this copper complex has a shape of uh, tetrahedral. Okay, so it's beryllium, and you have to draw a three-dimensional diagram. Okay, like this. This is how you draw a tetrahedral structure. So that's your three-dimensional diagram. Okay. Part D, explain why transition elements can form complex ion. Okay, why they form complex ion? Because the central metal ion is high has a high charge density, and d orbitals are energetically accessible. Okay, so you can write empty d orbitals are energetically acceptable. Okay, energetically accessible. Okay. Part 2, complete table 1.1 to show the coordination number of each metal ion and the shapes and overall polarity of the complex ion. So you are given cisplatin, that uh, platinum in this complex, and this is the uh, ethylamine. Okay, and this is bidentate ligand. Okay, so the coordination number will be 4. Okay, because the geometry is shape is a square planar, and in a square planar we have a coordination number of 4, and this will be a polar molecule. Okay, because the this en group and chlorine group have different polarities. Okay, they are not will cancel out the uh, each other's effect of polarity. Okay, so this molecule will be polar. Now there are two ammonia. Okay, so the ammonia is a monodentate ligand, so the coordination number is going to be 2, and this is non-polar. And uh, what is going to be the shape of it? It's going to be the linear shape. Okay, because there are only two ligands. Okay, so this will be like this. Okay, then we have a C2O4, and this is a bidentate ligand as this molecule. Okay, so and it also told you that it has a coordination number of 6. Okay, so 6 means it has a shape of octahedral. Octahedral. Okay, and since there is no other ligand, so the polarity will be cancelled out, so it will also be non-polar. Okay, party, define stability constant. Okay, so it is the equilibrium constant for the formation of complex. Okay, the equilibrium constant for the formation of the complex ion in a solvent, okay, in a solvent from its constituent ions, okay, from its constituent ions. So this is the definition of uh, stability constant. It's an equilibrium constant for the formation of complex in a solvent from its constituent ions. Okay. Part 2. Nickel can form complexes with ligands En, okay, and Tn, okay, as shown. The equilibrium 1 is shown and 2 is shown. Okay. The K stability value of these two are also shown. Construct an expression for the stability constant for the equilibrium 1, okay. Get the units. So this K stability is going to be it's going to be and by the way, in K stability, or we don't include water, okay, because the water is acting as a solvent, okay. So concentration of products divided by concentration of reactants, okay. So the product here is in equilibrium 1 is nickel, okay, concentration this divided by concentration of now the concentration of reactants, okay. So this is the concentration of reactants, and En, and the charge on En will be sorry, power on the En will be 3 because there are 3 moles of En, okay, En. So the power the moles in the equations will be power in the ASP expression, okay. And what are going to be the units, okay. So on in the numerator we have mole per dm cube only, because there is only a concentration of this nickel complex, and downward we have mole per dm cube multiplied by mole per dm cube power 3, okay. So this mole per dm cube is cancelled out, and then we have mole minus 3 dm cube power 9, okay. So these are the units: mole minus 3 dm minus dm power 9, okay. Now describe what the K stability value indicates about the position of equilibrium for the equilibrium 1 and 2. Use the K stability values to deduce which uh, complex with En or Tn is more stable. So the uh, K stability value actually shows you the stability of these complex, okay. And the greater the value of K stability, the greater the stable the complex is, okay. So the complex with En has more like K stability value, so this is going to be more stable, okay. And these values are highly positive, okay. So this shows that the equilibrium is lies to the left side, okay, on the product side. So we will write the equilibrium lies to the right side, okay. And En complex or nickel En 3, this complex ion is more stable because this has a greater K stability value, okay. Moving towards question number 2. Explain why transition elements have variable oxidation states. Okay, why they have variable oxidation states? Because the um, 3d and 4s orbitals are similar in energy. Okay, they have very smaller difference in their energies. Okay, so we will write the 3d and 4s subshells or orbitals are similar in energy. Okay, sketch the shape of dxy orbital. Okay, so this will be on the xy orbital. Okay, so firstly it's recommended that you draw only a sorry we will draw this x and the orbital dx y and z between x and y axis. Okay, so this is your y axis and this is your x axis, so the orbital will be like this and then like this. Okay, so this is your orbital on the x and y, between x and y orbital. Okay, part C, explain why transition elements form colored compounds. Why they form colored compounds? Okay, because the d splitting occurs and when an electron is excited. Okay, so the visible light a photon absorbs a particular wavelength of visible light, and the rest of the energy gives a complementary color. Okay, so in complex the d splitting the d orbitals are split into two sets of orbitals, two sets of orbitals. Okay, as an electron is excited. Okay, as an electron is excited, the d orbital is split into uh, two energy levels. Okay, into two sets of orbitals. Okay, and the photon which absorbs visible light. Okay, photon absorbs, yeah, or you can write that visible light visible light is absorbed by photon, and rest of the energy gives the complementary color. Okay, so this is your reason. Moving towards next question part, or sorry, part D. Aqueous solutions of copper to salts contain this complex of copper. Okay, equilibrium 3 and 4 show some reactions of these ions. Okay, state the color of this copper 2 hydroxide and this complex of copper. So this copper has a bilipipty, because when OH is ODed, so you have to remember the tests of copper 2 plus ion with NaOH and ammonia. Okay, when we add excess of ammonia, we get a deep blue solution. Okay, and when we add excess of sodium hydroxide, so we into copper 2 plus ion, we get a bilipipity. Okay, So that blue PPT is due to copper to hydroxide, and that dark blue solution or deep blue solution is due to this complex ion. Okay. So what is the color? Blue. And what is the color of this aqueous uh, complex ion? It's deep blue or dark blue. Okay. Use Le-Chatelier's principle to explain why a precipitate is formed when sodium hydroxide is added dropwise to this complex of copper. Okay, when sodium hydroxide is added, the concentration of OH ion will increase. Okay, so the when the concentration of reactants is increased, the equilibrium shifts to the right side. Okay, using the Le-Chatelier's principle. Okay, so when addition of OH ions, OH, sorry, so the addition of OH ions will increase concentration of OH ions. Okay, and equilibrium shifts to the right side. Okay, part E. There are two possible stereoisomers with the formula of this complex. Draw the three-dimensional diagram to show the two stereoisomerism. Okay, so there are six ligands. Okay, four ligands of ammonia and two ligands of water. Okay, so the shape will be octahedral in both. Okay, and as you can see, there are two two water ligands. Okay, so this will show this geometrical isomerism. Okay, cis and trans, and in cis molecule is a polar, and in which the polarity is not cancelled out. Okay, so in trans the polarity of is cancelled out and the bond angle is 180. So I'm going to draw the cis molecule first. Okay, so this is the cis molecule. Okay, and then we have a trans molecule, NH3. So how you can tell that this is a cis molecule and this is trans? Because you can see that the bond angle between water here is 180 degrees and the bond angle in water here is 90 degrees. Okay, and the polarity is not cancelled out. Okay, so the non-polar trans is a non-polar and the cis molecule is a polar. Okay, moving towards next question. Question number 3. Define first electron affinity. So it is the enthalpy change. Okay, so it is the enthalpy change when 1 mole of electrons is gained by 1 mole of gaseous atom. Okay, so enthalpy change when 1 mole of gaseous 1 mole of electrons, sorry, 1 mole of electrons is gained by 1 mole of gaseous atoms. Okay, the first electron affinity of an atom is usually an exothermic process, whereas the second electron affinity is an endothermic process. Why? Because when during the first electron affinity, an electron is gained, so it forms a negative ion. Okay, negatively charged ion, an anion. Okay, and for the second ionization energy, we have to add the another electron. So the electron has negative charge and the anion has also negative charge. So they will repel each other. Okay, that's why we have to give energy to overcome that repulsion. Okay, so what is the reason? The energy is required to overcome the repulsion between electron and anion. Okay, describe the general trend in the first electron affinity for Cl, Br, and iodine. Okay, so what is the trend? The first electron affinity, um, you can say it decreases down the group, because for the first electron affinity, the down the group, the shells increase, so the distance between nucleus and the valence electron is very large, so the nucleus attracts the incoming electron lessly. Okay, so less attraction between at a nucleus and incoming electron. Okay, so it decreases down the group. Okay, less negative or less exothermic down the group, less negative down the group. Why? because because atomic radius increase. Atomic radius increases, so there is more shielding factor increases. Okay, so less attraction between nucleus and incoming electron. Okay, that's the reason. Moving towards part B, table 3.1 shows the energy changes to be used in this question and in part C. Okay, okay, calculate the first electron affinity of for iodine. Use the relevant data from table 3.1 in your working, and it may be helpful to draw a labeled energy cycle. Okay, show all your working. Okay, so we have to calculate the first electron affinity of iodine. Okay, so we are giving the lattice and energy of zinc iodide. So we will start from this part. Okay, so what is the definition of lattice energy? Okay, it is the formation of an ionic compound from its gaseous ions. Okay, so when zinc 2 plus, gaseous zinc 2 plus, reacts with iodine, gaseous iodide ions, sorry, so it forms zinc iodide. Okay, there will be two iodide ions. So this is your lattice enthalpy. Okay, enthalpy change, and it has a value of negative of 26 minus 2605. Okay, now we can also calculate the enthalpy change of formation, and the and definition for enthalpy change of formation is um, formation of ionic compound from its elements under the standard states. So standard on states at room temperature, and the zinc is solid at room temperature, and iodine is also solid at room temperature. Okay, so from this you can actually form uh, zinc iodide. So this will be the enthalpy change of formation, and see if you are given the enthalpy change of formation. Yes, standard enthalpy change of formation of zinc iodide is also given to you, which is negative 208. Okay, now to convert this zinc solid into zinc 2 plus ion, first we have to atomize it. Okay, and when it is atomized, it is turned into gaseous zinc. Then there is first ionization energy, so it will form zinc plus ion. Then there will be second ionization energy, so it will form zinc 2 plus. Okay, this will be in gaseous form. Okay, and for iodine you have to first uh, convert this iodine um, into the you have to yes, enthalpy change of sublimation. You are given enthalpy change of sublimation of iodine. Okay, so firstly you will make it gaseous in a gaseous state. Okay, gaseous form. Okay, then you will break this bond, this iodine bond, and the bond energy of this II bond is given to you, which is 151. Okay, so this will form 2I. Okay, and then there is the first electron affinity of iodine. Okay, which you have to calculate. So I'm writing this as X, and this will be 2X because there are two iodide ions formed. Okay, from two iodines. Okay, so 2X. So now this cycle is ready. We just have to put the uh, these values here. Okay, so let's do this. For zinc, to convert zinc into solid zinc into gaseous zinc, this is the enthalpy change of atomization of zinc. Okay, which is 131. So 131 plus then the first ionization energy of zinc, which is 906. Okay, 906. Then we have second ionization energy of zinc, which is 1733 plus 1733. Okay, then we have plus, we will uh, put the arrows which are head to tail and in the one side and the other on the other side. Okay, so to change iodine, sublime iodine, we have enthalpy change of sublimation of iodine, which is 62. Okay, plus the bond energy of iodine, okay, which is 151. Plus we have then the first electron affinity of iodine, which we have to calculate. So I am writing this as 2X. Then we have the finally enthalpy, lattice enthalpy of zinc iodide, which is uh, negative of 2605. Okay, which is, this is all equals to minus 208. Okay, so from here you will get the value of x. X is equals to negative of 293, and this is your final answer. I hope you understand this, how to calculate this first electron affinity of iodine. Okay, predict how the lattice enthalpy of this iodide. Okay, which is what is this CD? If you see this symbol, um, this yes, this is cadmium. Okay, if I zoom in, this is cadmium and this is your zinc. Okay, so how predict how the lattice enthalpy of cadmium iodide differs from the lattice enthalpy of zinc iodide? Place a tick. So you can see from the periodic table, the cadmium is down the zinc, okay, and down the groups, the charge density of metal ions decrease because the scale increases, okay, and the atomic radius increases, okay. So so there is a less charge density down the group, so cadmium will be less negative, okay, than the zinc iodide, okay. Why? Because the cadmium 2 plus is larger or has lower charge density, okay. Cadmium 2 plus has lower charge density, so lower charge density, okay. So less attraction between the ions. Moving towards next question, question number 4. Calcium carbonate decomposes on heating, okay. Table 4.1 shows the values for the Gibbs free energy for this reaction at various temperatures, okay. Assume that the standard enthalpy change and the standard entropy change for this reaction remains constant over this range of temperature. Use the data in table 4.1 to plot a graph of Gibbs free energy against time on the grid. I already drawn this graph for you. Um, it may not be as accurate, but it will be like this. Okay, I have drawn this already. Okay, then we have second part, calculate the gradient of your graph. Okay, determine the value of uh, this entropy change in joule per Kelvin per mole for this reaction. So all your working. So if you write the equation of Gibbs free energy, for suppose Gibbs free energy is equals to enthalpy change negative of um, temperature and enthalpy change of sorry, entropy change. So if I rearrange the equation, we will have negative of Ts plus enthalpy change, and if I further rearrange it, so we will have negative of entropy change T plus enthalpy change, and you can compare it with y is equals to mx plus c. So m is the gradient, okay. So if you calculate the gradient, this is going to be the m is equals to entropy change, okay. So that's why I told you that determine the entropy change. So if you calculate the gradient, you will this that will be your entropy change, okay. Gradient is equals to negative of entropy change, okay. So if you calculate the gradient will be negative because the slope is decreasing, you can see that, okay. So the gradient will be give you the entropy change. So I think you can calculate gradient very easily from this formula. M is equals to y2 minus y1 upon x2 minus x1, okay. I don't think I need to do this part, okay. But the answer and marking scheme is plus 160 and with uncertainty of 10, okay. Your answer should be in this range, okay. So I think you can do this by your own, okay. I'm moving to next part. Part B. Group 2,1 hydrogen carbonates decompose on gentle heating to give the corresponding metal carbonate, carbon dioxide, and water vapors. Write an ionic equation for the decomposition of hydrogen carbonate ion. Okay, so hydrogen carbonate ion has a formula of this HCO3 minus. So when it decomposes, it forms a metal carbonate, so means carbonate ion 2 minus plus carbon dioxide plus water. Okay, so balance the equation like this. Okay, the thermal stability of group 1 hydrogen carbonates increase down the group. Suggest an explanation for the trend in this in the thermal stability of the group 1 hydrogen carbonates. Okay, why the this increase stability, thermal stability increase down the group? Because down the group the cationic radius increase, so the charge density of metal ion decrease, so there is less polarization of anion. Okay, and when there is less polarization, it means the bond is strong. So you can write cationic radius increase increases. Okay, so there there is less polarization of anion, or you can write this hydrogen carbonate ion. Okay, part C. The buffer system in seawater contains the mixture of CH, this hydrogen carbonate ion, and this hydrogen carbonate. Okay, CH2 H2CO3. Okay, equilibrium 5 is shown to you. Define a buffer solution. So a solution which resists change in pH um, when small amount of acid or base is added. Okay, solution which resists change in pH when small amount small in pH when small amount of acid or base or alkali is added. Okay, construct two equations to show how the equilibrium 5 acts as a buffer solution. So I will react this equilibrium 5 with acid and base. So when this hydrogen carbonate ion is reacted with H plus, because in acid we have H plus ions, so it will form H2CO3. Okay, and when this H2CO3 is reacted with OH, it will form hydrogen carbonate ion plus water. Okay, so that's why this is acting as a buffer solution. Part 3. The concentration of hydrogen carbonate and divided by this H2CO3 ratio in a sample of seawater is 14.1. Okay, so calculate the pH of this sample. So we have to calculate the pH of this sample. Okay, so and the pKa of H2CO3 is shown. And this is Ka is used for acid dissociation constant, and it is for the weak acids. Okay, so for the this ratio, you can write this expression H2CO3 when this this is the dissociation constant. When this is dissociated, it forms H plus ions plus hydrogen carbonate ions. Okay, so this is the expression for the acid dissociation constant. Okay, and we have to calculate the pH of this sample. pKa is given to you. Okay, now if this is acting as a buffer solution, this is we have to calculate the pH of buffer solution. Okay, so we let's say we form a salt of this sodium hydrogen carbonate. Okay, so sodium hydrogen carbonate, when this decompose, it will form sodium plus ions plus hydrogen carbonate ions. Okay, so the expression for the Ka has an expression of H plus ions, concentration of H plus ions, then concentration of hydrogen carbonate ions divided by concentration of acid. Okay, and from these two equations, you can see that this reaction is reversible and this is a direct reaction. So it will all this sodium hydrogen carbonate will decompose into this uh, hydrogen carbonate ions. Okay, so if X concentration of sodium hydrogen carbonate is X, so the hydrogen carbonate ion will also have a concentration of X. Okay, and here this concentration of H plus ions is not equal to concentration of hydrogen carbonate ion, because uh, hydrogen carbonate is more here. Okay, so but the concentration of hydrogen carbonate is equals to sodium hydrogen carbonate, because this hydrogen carbonate is very less. Okay, so we don't consider it. So we imagine that this concentration of hydrogen carbonate ion is equals to this concentration of salt. Okay, so from there, if I write the expression again, so we have to calculate the H plus ion. Okay, concentration of H plus ions. So we will have Ka multiplied by concentration of acid, divided by concentration of salt. Okay, so you are given the ratio. So let's say don't write it as a salt. Okay, I am writing it as hydrogen carbonate. Sorry. So you are given the ratio of this hydrogen carbonate. Okay, which is 14.1. So if I rewrite this here, so H plus ion is equals multiply by 14.1. Okay, this is your expression. Okay, and you can calculate the H plus ions by Ka divided by 14.1. Okay, now you have to calculate the Ka, and you are given pKa. So to calculate pKa is equals to minus log 10 of Ka, and Ka is equals to 10 minus pKa. Okay, so the 10 minus 6.35 divided by 14.1 is equals to concentration of H plus ions. Okay, so from here you will get the concentration of H plus ions as 3.17 into 10 to power minus 8. Okay, and now you have the concentration of H plus ions, so you have to calculate pH is equals to minus log of 10 of H plus ions. Okay, so you will have minus log 10 of 3.17 3.17 into 10 to power minus 8. So it will give you the pH of 7.5. Okay. The marking scheme has also given you an alternative method, and you can also calculate this uh, pH by formula of buffer solution. This formula pH is equals to pKa plus log of concentration of salt divided by concentration of acid. Okay, this formula can also be used. Okay, and this and there you have the value of pKa 6.35 and plus the salt is the concentration of salt is equals to concentration of hydrogen carbonate. So and the hydrogen carbonate concentration of hydrogen carbonate and this acid has a ratio of 14.1. So this is going to be a log of uh, log 14.1 divided by 1. So this will be 6.3 plus log of 14.1, and from here you will get the pH is going to be 7.5. Okay, this method can be used to check if your answer is correct, but I would suggest to go with this method because it has more steps, so the you will get full marks. Okay, this process has very less few steps, so your marks may be deducted. Okay. Question number 5. Complete table 5.1 to predict the substance liberated at each electrode during the electrolysis of indicated electrolyte with inert electrodes. Inert electrodes are used. So electrolyte is a molten, because in liquid form, so molten lead bromide. So what will be liberated? This is a molten, so no other ions are present. So what will be liberated at anode? An anion is liberated at anode. So the bromine will be liberated at anode, and the lead will be liberated at cathode. Now the concentrated NaCl. So in concentrated you have sodium plus ions, Cl minus ions, and water ions of water. And at anode you see if an halogen is present, then the halogen is liberated. Otherwise OH ion will liberate and it will form oxygen. Okay, so what be liberated here? There will be a chlorine, because a halogen is present. And at cathode we see the reactivity. The less reactive element will liberate. Okay, and hydrogen at H plus ions are less reactive than sodium, so hydrogen will liberate. And how I know that this sodium is more reactive and hydrogen is less reactive? This is by reactivity series, which you have to remember. Okay, this you have to remember because this reactivity is used in O levels in IGCSE as well. Okay, so this is the reactivity, you have to remember this. Okay, I also I also showed you the way how you can remember this. Please stop calling me a careless zebra. Instead, try learning how copper saves gold. You can make this uh, sentence or any other sentence like this to remember this reactivity series. Okay, so you can see that the sodium is more reactive than hydrogen. Okay, most reactive. Reactivity increase upwards. Okay, so sodium is more reactive and hydrogen is less reactive. So the less reactive metal is liberated at cathode, because the more reactive will not reduce. Okay, so and then we have third, copper nitrate. So this is when you are not given dilute, it means the solution is so you are not given concentrated, so it means the solution aqueous solution is dilute. So in dilute solution you have copper ions of copper 2 plus, then nitrate ions, and you have ions of water. So in this, the uh, ions of OH are in greater concentration because water is in excess. This is dilute solution. Okay, so OH ion will go and it will form oxygen, and on the cathode we will see reactivity like we did in this concentrated NaCl. So copper is less reactive. Okay, so the copper will be liberated. Okay, copper solid. Moving towards next question part B. An electrolytic cell is set up to determine the value of for Avogadro's constant. Okay, the electrolyte is dilute sulfuric acid, and both electrodes are copper. Okay, so copper electrodes are not inert. You have to remember that. When a current of 0.61 ampere is passed through the acid for 30 minutes, the anode decreases in mass by 0.35 grams. Okay, state the relation between Faraday's constant F and Avogadro's constant. So the relation is F is equals to L E. Okay, and where E is charge on one electron. Okay, 1.6 into 10 to power minus 19. Okay, so this is the relation, and this is the formula for the Faraday's constant. You have to remember this. Okay, and from important values you can also get the value of E, which is electronic charge. Okay, now part 2. Use the experimental information in B1 and B and data from the table on page 23 to calculate this value for the Avogadro's constant. So the table on page 23 is the important values. Okay, this 23 is of important values. Okay, use the to calculate the value for the Avogadro's constant. So now you might wonder that we are giving the value of Avogadro's constant in these important values. So, but you will not write this value, and we have to calculate by experimentally. Okay, because we are given some data, yeah, and we have to calculate the value for the Avogadro's constant experimentally, and there will be a note will be as note will be like the value in the uh, value in this table. Okay, there will be uncertainty. Okay, so the value will be little different. Okay, so now let's begin. What is happening here? The anode mass of anode is decreasing because there is oxidation at anode, so the copper electrode will at anode will decompose, sorry, it will change into copper 2 plus ions plus, and 2 electrons will be released. Okay, this is the reaction at cathode. Okay, now for what is you have to first calculate the charge. Okay, we are given ampere current and time. Okay, so q is equals to it, and I is equals to 0.6 multiplied by time, but time should be in seconds and there are in minutes, so we have will multiply it with 60, so there is 108 coulombs. Okay, this is your charge. Now the mass of anode decreased by mass n 0.35, so let's convert this into mole. So n moles of copper 2 plus ions, n of copper 2 plus ions is equals to 0.35 gram divided by the mass of copper, which is you can see from this periodic table, the mass of copper is 63.5. Okay, so 63.5, and you will get the value of 5.51 into 10 to power minus 3 moles. Okay, so If let's now make the ratio. If 5.5 1 mole per into 10 to the power minus 3 moles have a charge of 1081, then what will be the charge on 1 mole? Okay, 1 mole of electrons. Okay, sorry, charge on this 1 mole of copper 2 plus ions. Okay, so the charge on x plus will be x. So by uh, ratio cross multiplication, we will have the value of x is as 1080 divided by 5.51 into 10 to the power minus 3. So you will have a value of 1919663.6 coulombs. Okay, this will be the charge on 1 mole of copper 2 plus ions. Okay, now this charge, let's calculate the charge on 1 mole of electron, because there are 2 moles of electrons. So for the 1 mole of electrons, charge on 1 mole of electron, what will the charge on 1 mole of electron? So let's divide it with 2. 19636.6 coulombs divided by 2. So you will have a value of 98181.8 coulombs per mole. Okay, this is your Faraday's constant. You have given the value of Faraday's constant here as well, which is 9.65 into 10 to the power minus 4, which is 96500. So this value and this our experiment values are different because there is a uncertainty in this value. Okay, so but we will be dealing with this which we have calculated. Okay, so now that you have calculated the value of f, and f is equals to L E, so from here you will get the value of L, which is f upon E, and f is 98181.8 divided by what is the charge on one electron E, which is 1.6 into 10 to the power minus 19, which you can take from important values. Okay, E, we don't have to calculate E by this experimental. Okay, we will take it from this important values table. Okay, so from here you will have a value of L, which will be 6.12 into 10 to the power 23. Okay, so you can see that this value is little different from this important value in the L in the important table. This is 6.02 and this is 6.12. But we will consider this as right, because we know that our value is very close to the actual value. Okay, so this is your answer. And marking scheme, it it uh, it, it has done by different method. Okay, it calculated this value of L by different method. So let's explain that method as well. Okay, I that method is also correct and this method is also correct. Okay, and marking scheme, it first calculate the value of number of moles of copper, which is 5.51 into 10 to the power minus 3, then value of Q, which is 1080. Now it calculated the value of number of moles of number of electrons. So the charge on one electron has a charge of 1.69 into 10 to the power minus 19, and the total charge is 1080. So now you can calculate the number of electrons. Number of electrons is equals to total charge divided by charge on one electron. Okay, So you will have a number of electrons is equals to 6.75 into 10 to power 21. Okay, this is your number of electrons, and now you will calculate number of copper 2 plus ions. Okay, so you will divide this with 2, so you will get this 3.37 into 10 to power 21. Okay, now you have a number of copper atoms, copper ions, sorry, copper 2 plus ions. Now you have to calculate this number of copper 2 ions per mole, which is your Avogadro's constant. Okay, Avogadro's constant is a number of atoms or ions per mole. Okay, so 3.37 into 10 to power 21, and your moles are this moles of copper 2 plus ions, which is 5.51 into 10 to power 10 to power minus 3. Okay, so you will have a value of 6.12 into 10 to power 23. This method is also correct. Okay, I thought I could explain this method to you as well. Okay, so that's all for the day, and from question number 6 the organic chemistry starts, and we will deal with these questions in this next part. Okay, I hope you are clear with these questions, and we will do other questions in the next part. So till then, uh, take care, and thanks for watching. And if you haven't subscribed my YouTube channel, do subscribe. Okay, thank you.